This video will take a look at the A-star algorithm. Now, in the previous video we looked at Dijkstra's shortest path algorithm, and it was brilliant. It allowed us to methodically work out the shortest distance between a node and all other nodes. Now, one of the disadvantages of Dijkstra's shortest path algorithm is that it has to visit every node before it completes its job. It has to exhaust every single pathway. And in real life, if you think about it, if you wanted to go from A to B and you looked at a map and you looked at possible different routes to get from A to B, you might be able to see very, very quickly that some pathways just aren't worth investigating. They're clearly far too long, far longer than other pathways. But the problem is that algorithms don't have this human insight. They can't just have a look at a map and go, oh, I don't need to bother with that because that's clearly too long. So as we saw with Dijkstra's shortest path algorithm, every pathway had to be exhausted before it came up with the shortest path. Now, the good news is that a new algorithm, the A-star algorithm, I say new, I mean newer than Dijkstra's, basically makes use of heuristics. Heuristics being this idea that perhaps we're not going to find the perfect solution, but we will find a solution that is good enough. So it makes use of heuristics to actually be able to work out that some pathways just aren't worth investigating, therefore speeding up the shortest path algorithm. So the A-star algorithm is built on top of Dijkstra's. So it's basically Dijkstra's shortest path algorithm with some added benefits. So the A-star algorithm, like I said, it's a slight variation on Dijkstra's algorithm, which makes use of heuristics to increase the algorithm's efficiency. So let's take a look at how it works. So if you consider the following graph, we've got different nodes that are connected to other nodes, and we've got the distances between the nodes on the lines that connect them. Now, with the A-star algorithm, we also use one more measurement. What we use is the straight line distance from each node to the destination node. So if you think about it, before I show this on the graph, to get from this node on the left, if we were to use the top pathway, we would have to go 3 plus 5 plus 6. So we'd have to go 14 to get to the destination node. Now, what we also look at is the distance as the crow flies from each node to the end. So that is represented by these red lines. So the straight line distance, the distance as the crow flies, it's not the real distance. The real distance, you'd have to go through different nodes to get to the destination node. But the straight line distance is used to allow the algorithm to work out that some pathways just may not be worth investigating. So they're shown in red. So above each of the nodes, you've got another red number, or another number which is red, and they are the straight line distances. So why is this important? Well, this additional information is what enables the A-star algorithm to make use of heuristics, because this algorithm, as it visits each of the nodes, works out not only the distance from the start, but also the shortest possible distance to the end node. And by considering both of these things, when comparing possible pathways, what the algorithm can sometimes do is disregard certain pathways that it doesn't need to investigate, simply because a node's shortest possible distance to the end, for example the red line, may already be further than another pathway that's been investigated. So let's have a look at an exam question, an exam style question, to see how we could actually work our way through the A-star algorithm to find the shortest path, and perhaps gain a little bit more insight into how certain pathways don't need to therefore be investigated by using these straight line distances. Okay, so here's an exam question. Use the A-star algorithm to work out the shortest route from A to F. So we've got a graph down here, and we want to go from A to F. We've got different possible pathways. We could go A, B, E, F. We could go A, C, E, F. We could go A, C, D, F. So let's have a look. If we were to do Dijkstra's shortest path algorithm, every single pathway would have to be investigated, but let's see if the A-star algorithm allows us to get to the solution quicker. So how do we do it? Well, like I said before, it is Dijkstra's shortest path algorithm with a few extras. So it's the same process that you would have seen in the previous video. We create a queue of all nodes from the starting node at the front and add each of their distances from the starting node. Heuristic distances to the end node and their sum. So those two extra points are extra things that we would add in the A-star when we're working out the shortest path using the A-star algorithm. Dijkstra's would simply list the different nodes and their distances from the start. So to get from A to A, well, that's 0. To get from B to A to B, that'll be at the moment infinity because we haven't investigated yet. The same for C to A, D to A, E to A, and F to A. But the extra things that we add in are these two values here, H and S. Now H is the heuristic value. It is the straight line distance. So the straight line distance to get from A to F is 80, and that's shown by the number above the node. To get from B to F, the straight line distance is 90. You can see that the red number is underneath B. To go from E to F, straight line distance would be 20. D to F would be 50. C to F would be 70. So we update the H values, the heuristic values, and then what we do is we add them together. Okay, we add the real distance and the heuristic distance to the end. So the real distance from the start and the heuristic distance to the end, we add them together to get our sum. So 0 plus 80 is 80, infinity plus 90, well, that's infinity, and that continues for the others. So we start off our queue like so. Then what we do is we remove the front node and we add it to the visited list along with its distance from the starting node. Remember that when it comes down, we are only interested in the actual distance from the start. So in this case, to get from A to A at 0, we say that we visited it, and then we start to have a look at the nodes connected to A. So A is connected to C and connected to B. So what we do is we update our list, and you can see here that we've updated C with the actual distance from A to be 25, the heuristic distance from C to the end to F is being 70, and the sum of those two things is 95. When we update B, the actual distance from A to B is 210, the heuristic distance from B to the end is 90, we add them together to get the sum of 300. And then what we do is we make sure that they are ordered. So just like with Dijkstra's shortest path algorithm, we would order the queue. It would be a priority queue where the shortest distance always goes first. But in this case, the shortest distance that we're focusing on is the sum. And you can see that this is in the correct order, so that's fine. So what we now do is we say, okay, well, we've investigated all the things connected to A. C is at the front. So we say that we drop C down into our visited nodes list, and now we start investigating the nodes connected to C. Well, to go, the nodes connected to C are D and E. So we update D's values and we update E's values. So D's value, well, to get from A to C to D, well, to get from A to C was 25, to get from C to D is 51, add them together and you get 76 as being the real distance. The heuristic distance from D to the end is 50, we add them together to get 126. We do the same with E. To get from A to C was 25, to get from C to E is 176, add them together and you get 201. The heuristic distance from E to the end is 20, we add them together to get 221. We've now visited all the things attached to C. We now need to reorder this list, or this queue, so it's priority queue. The sum, the smallest sum value goes to the front. So we reorder it, so D's at the front, and we now drop D down into our visited nodes list. So we're at D, and we're now going to investigate the nodes that are attached to D. Well, we already know that to get to D, it's 76 from A. To go then on to F, it's 307. So we add that. So we add the two together, so 76 plus 307, and we put that down to the P distance, the actual distance, 383. Now the heuristic distance to get from F to F is 0, so therefore the sum is 383. That pathway has now been worked out at 383. The sums are in the correct order, so what we would now do is drop E down as our visited nodes list and investigate the nodes attached to E. Now what's important here is that the A-star algorithm has worked out one pathway already. It's now got potentially 2 more pathways to work out before it comes up with the shortest path. Now that's certainly what would happen with Dijkstra's, but let's see if the A-star algorithm can get to the solution faster. So as I said, E comes down to the visited nodes list. So we go to E and we look at all the things that are connected to E. Well, what's connected to E? Well, we can go to B. Now, if you think about the fact that we've already gone 201 to get to E, we need to add another 233 to get to B. Well, that's already far greater than the S value here, and certainly the P value here, sorry. So therefore, we won't update B's values. And let's have a look to see if how far we need to go to F. Well, to get from A to E via C, we've already worked that out as being 201. To then get to F, you can see that we would need to add 185. Now if you added 185, you would get 386, which is longer than the value that we've already worked out. So what we are able to do is we're able to ignore that pathway, so therefore E is not part of the route. Therefore we don't need to investigate the pathway via B, and what we'll do is we'll be left with a list of nodes that are relevant to the route that we're trying to find and their distances from the starting node. Notice that in this case, okay, B doesn't get added to the visited list. Okay, it doesn't need to be visited as the A-star algorithm using heuristics discovered a shorter route. So therefore the shortest path from A to E is A to F, it should be, is 383. So and we can use the route A, C, D and F for that.